In this lesson, we're going to look at the gyroscopes on the INS platform and how they need to be corrected. However, we'll start by reminding ourselves about the data flow in INS from the last lesson. We have a north and an east accelerometer. They sense every change of aircraft movement and pass it to first stage integrators. The first stage integrators continuously add up these accelerations, thereby converting them to velocities. The velocities are used to calculate track and ground speed. And they are also passed to second stage integrators where they are converted to distance gone. The northerly distance gone is simply added to the initial position to generate a new latitude. However, the easterly distance gone has to be converted to change of longitude. We need an input of latitude. Fortunately, we already have it. It is the current latitude part of present position in the display. The latitude is therefore passed to a secant multiplier. This converts it to change of longitude, which is added to the initial position to generate a new longitude. Because of the speed at which computers operate, this process is repeated many times a second. We therefore have a continuously updated present position. Accelerometers are quite similar in principle to a spirit level. Suppose you were to jerk a spirit level sharply to the right. The bubble would move because of the inertia of the liquid. But what would happen if the spirit level were not perfectly horizontal? The bubble would also move. How can you tell the difference? The answer is that you can't. You have no way of knowing what's causing it. Exactly the same problem applies to an accelerometer. It's designed to sense lateral accelerations when it's on the level. There is no problem because g, the gravity vector, is at 90 degrees to the sensitive axis and so is not sensed by it. However, if the accelerometer is on the tilt by an angle of, say, theta, the sensitive axis will pick up a component of gravity of g sine theta, even if the aircraft is on chocks and not going anywhere. This would be disastrous. As we said, the integrators would not know that these false accelerations were really components of gravity and would start integrating them, thereby generating false velocities. A constant acceleration would very rapidly build up into a very large velocity. Think what happens when you hold the accelerator pedal down on your car. These rapidly increasing velocities would then be passed to the second stage integrators, where they would very rapidly build up into distances gone. We would have a runaway system, all this whilst the aircraft is still on chocks. This must not be allowed to happen. The solution is to keep the accelerometers level. The accelerometers are therefore mounted on a platform, which is kept level by tying it to a gyro. In fact, there are 3 gyros, not 1. And all of them are horizontal axis gyros. We need to modify our previous diagram of data flow in order to incorporate these changes. However, in order to keep the diagram simpler, we will show only the north channel. Precisely the same modifications are necessary in the east channel, but we are not showing them in order to avoid duplication. Although there are 3 gyros and they are actually horizontal axis, we will diagrammatically show only one and we'll show it vertical axis to make it clear that its job is to keep the platform horizontal, just like an artificial horizon. The types of gyro used in INS can either be rate integrating gyros or 2 degree of freedom displacement gyros. Rate integrating gyros are widely used. The rate integrating gyroscope is a single degree of freedom gyro using viscous rather than spring restraint. However, the details of its construction need not concern us. We should simply note that, although mechanically it is a single degree of freedom system, because of the integration process, its output behaves as though it were a 2-degree of freedom system. The gyroscopes are not mechanically tied to the airframe or to gravity, and would be space gyroscopes, having no mechanism to tie them to correct for real wander. However, mathematically computed corrections for apparent wander, that is, Earth rate and transport wander, are applied. Space gyros remain orientated to a fixed point in space. But the whole purpose of INS gyros is to keep the platform level to local Earth, but without using gravity as a sensor. This means that corrections for gyro wander need to be applied. The broad subdivisions of gyro wander are into real and apparent. Real wander is caused by mechanical imperfections, such as gimbal friction or rotor imbalance. Unlike apparent wander, the spin axis is actually moving with respect to space. Real wander is minimized by high-quality engineering and manufacturing techniques. These techniques are expensive, requiring special metals, jeweled bearings, liquid sealing, clean rooms with airlocks, and other high-technology methods. However, when the money is spent, real drift rates of around 1/100th of a degree per hour were typical for 1970s tuned rotor gyros. It can therefore be said that, with INS technology, real wander is so low that the gyros can almost be regarded as ideal gyros. This leaves us with apparent wander. You will remember that this is split into Earth rate and transport wander. They are both needed to stabilise the platform. We need to examine Earth rate in more detail to understand how INS alignment takes place, why it takes so long, and why the aircraft cannot be moved whilst it is happening. We also need to examine transport wander in more detail to understand how some types of INS errors are caused and why they have a sinusoidal waveform. These are the well-known Schuler errors. The way the Earth rate varies with latitude will depend on whether it is the horizontal component or the vertical component of Earth rate which is being considered. We'll start by considering the horizontal component. Imagine an aircraft parked on the equator with the gyro axis pointing to true north, that is, aligned with the local meridian. As the Earth rotates from position 1 to position 2, the gyro axis remains fixed in space and also remains aligned with the local meridian. At the equator, the gyro direction has not changed with respect to Earth direction. It is still pointing in a direction parallel to the original one, which is true north. Earth rate is therefore 0. However, in this picture we are looking down on the North Pole. The gyro and the meridian are in line. As the Earth rotates, the meridian changes its direction with respect to space, but the gyro does not. This gives us an equation for the horizontal component of Earth rate, which we have met before. It's 15 times the sine value of the latitude in degrees per hour. Now, let's look at the vertical component of Earth rate. You have to understand this in order to appreciate how alignment takes place and why it becomes difficult or impossible at high latitudes. We are looking down onto the North Pole and the aircraft is parked at the equator with the gyro running. The wings are level and the gyro axis defines the horizontal, or wings level. The Earth then rotates, taking the aircraft with it, to position 2. The gyro, being rigid in space, has retained its space orientation. The orientation of the aircraft to the gyro has changed by 90 degrees, and the gyro is now indicating 90 degrees of bank. So, at the equator, we get the full 15 degrees per hour of vertical component of Earth rate. Now the aircraft is at the North Pole, or latitude 90, and we are looking at the Earth from sideways on. As before, the wings are level, and the gyro axis defines the horizontal, or wings level. In this case, no matter what the rotation of the Earth, there will be no change in indicated bank angle. Earth rotation will give apparent yaw but no apparent bank. So, at the pole, we get 0 degrees per hour vertical component of Earth rate. The cosine of 0, or the latitude of the equator, is 1. The cosine of 90 degrees, or the latitude of the pole, is 0. This gives us an equation for the vertical component of Earth rate. It's 15 times the cosine of the latitude in degrees per hour. Corrections for Earth rate based on the sine and cosine of the latitude therefore need to be computed and passed back to the platform in order to keep it level as the Earth rotates. Fortunately, latitude is being constantly updated in the North Channel. All we have to do is constantly feed the latitude to a computer which continuously calculates 15 degrees times sine latitude and 15 degrees times cosine latitude per hour, and pass it to the appropriate channel of the platform. As with Earth rate, there are two components of transport wander, horizontal and vertical. Let's start with horizontal. We've seen this before. Although transport wander takes place at the same time as Earth rate, we shall explain them separately for simplicity. So, disregarding Earth rate for a moment, imagine the Earth stopped in space, not rotating. We have an aircraft at Los Angeles with its gyro aligned with north up the local meridian. This is the solid white line. The aircraft flies from Los Angeles to London. When the aircraft arrives in London, the gyro is still aligned with the same direction in space, the dotted white line. However, the actual direction of true north from London is the line connecting London to the North Pole. The difference is the horizontal component of transport wander, which is in fact the difference in the alignment of the meridians at Los Angeles and London. Horizontal transport wander is actually meridian convergence. There is an equation which we have met before. The horizontal component of transport wander is u over 60 times tangent of latitude. Again, we can continuously calculate this correction by computing. We already have u in the east channel, and a continuously updated latitude in the north channel. So, similarly to the way we did before, we can feed a continuously changing value of u and another continuously changing value of latitude to a computer, which continuously calculates u over 60 times tangent latitude, and passes it to the appropriate channel of the platform. So, we're now on to the correction for vertical component of transport wander. This is also known as Schuler tuning. It has nothing to do with Earth spin. It is because, as we travel over the Earth, the gyro would remain fixed in space. But the local direction of the horizontal changes. Our accelerometers are affected by gravity, and they must be kept horizontal to local gravity. The traditional way of keeping gyros and instruments level is by using gravity, for instance, by using mercury gravity switches. But as we've pointed out before, the accelerometers themselves would be the best choice for gravity sensors. However, they are being used for sensing horizontal acceleration. Like the spirit level, you can't use the same device to give you both gravity and accelerations. It's one or the other. So we continue to use the accelerometers to measure horizontal accelerations, and we have to find another way to keep the platform at right angles to the gravity vector. As you might expect by now, a mathematical method is used. Here's a picture of an aircraft at the equator, along with the local horizon at the equator and the radius of the Earth. The aircraft now flies, say, 60 nautical miles northwards. The horizon has changed. Knowing the distance d and the Earth's radius, we can work out the angle theta, which is the amount of change of horizon. it would be tangent of theta equals d over r. If you do the sums, it comes to exactly 1 degree. This is what you would expect from a change of 60 nautical miles directly northwards. However, in reality, it would not be sensible to wait till the aircraft had flown a distance before feeding in a correction to the gyro. The gyro attitude should be adjusted as soon as the aircraft starts to travel. Therefore, instead of using d, the distance gone in the above equation, we take v, the velocity, northwards and use it to find omega, the angular velocity. Omega is the rate at which we need to correct the platform. It will be a value in degrees per hour. The equation now becomes omega equals v over r. We know r, the radius of the Earth. Its average value is 3,437.7 nautical miles. To find omega, we need v, but we already have it. It is coming out of the first stage north-south integrator. All we have to do is take a parallel value out of this source and divide it by r, then feed it back to the gyro, like this. There are, in fact, 2 feedback loops, one in the north channel, the v over r loop, which keeps the platform level as the aircraft flies around the Earth northwards or southwards. There is also a u over r loop in the east channel to keep the platform level as the aircraft flies around the Earth eastwards or westwards. Schuler tuning is, in fact, an electromechanical velocity feedback loop, as shown here. The purpose is to keep the platform level with the local horizon as the aircraft travels around the Earth. However, some people find it helpful to imagine a huge pendulum with a length equal to the Earth's radius, with the platform bolted on at right angles. The bob of the pendulum remains at the centre of the Earth. Then, as the aircraft travels, the circular motion of the rigid part of the pendulum keeps the platform level. This pendulum analogy is more helpful when considering the nature of Schuler errors, which we will come on to in a future lesson. Let's look at the full list of platform corrections now. Some have been met before, but 2 of them will be new. These 2 don't need to be understood in such detail. Firstly, there is the correction for aircraft manoeuvres. You'll remember that the platform has to be kept north-orientated. Level in pitch and in roll. Next is earth rate. The sine and cosine of latitude are continuously computed and fed back to the platform. There is transport wander. The horizontal component is corrected by continuously computing u over 60 tan latitude and feeding it back to the platform. And the vertical component is corrected by the v over r and the u over r feedback loops, otherwise known as Schuler tuning. The first of our new ones is Coriolis. Here's a simple explanation. You're flying down a meridian towards the equator in the northern hemisphere. Your direction with respect to Earth is due south. But the Earth is rotating. So your track with respect to space is curved. If you're flying a curved path in space, there must be an acceleration into the centre of the curve. This can be calculated and allowed for. And finally, there is central acceleration. Again, a very simple explanation. Imagine yourself flying around the Earth. If you really were travelling in a straight line, you'd disappear off into space. Clearly, that doesn't happen. There must be a force accelerating you into the centre of the Earth. Again, that has to be calculated and allowed for. So, To summarise, the full list of platform corrections is aircraft manoeuvres, earth rate, transport wander, Coriolis, and central acceleration. Now that we see the need for Schuler tuning, we can look at the full data flow, including the V/R feedback loop. The accelerometer is mounted on a platform which is stabilised and north-orientated by gyroscopes. It detects accelerations which are passed to the first stage integrator. Here they are integrated into velocity. One feed of this velocity is taken forward to the second stage integrator, where it is converted to distance gone and added to the present position, thereby generating a new present position. A parallel feed of the velocity is fed backwards through a V/R feedback loop, where it is converted to the omega term which is used to rotate the gyro to keep the platform perpendicular to the local gravity vector. The same sequence is taking place simultaneously in the east channel, the only difference being the addition of a secant multiplier to convert SE into change of longitude. There have been very few new ideas in this lesson. We have met most of them before. What makes this lesson important is the way they interact. So we'll summarise what we've covered. Firstly, we revised the basic data flow without Schuler tuning. Then we saw that, like spirit levels, accelerometers can't distinguish between being accelerated horizontally and being tilted. We therefore have to mount the accelerometers onto a platform and keep it horizontal to the gravity vector by using gyros. Modern, expensive manufacturing techniques have made real wander so low that the gyros can be regarded as almost perfect. However, that still leaves apparent wander. Earth rate is corrected by calculating the sine and cosine of latitude and using them to precess the gyros. The horizontal component of transport wander, or meridian convergence, is also corrected by calculation. The vertical component is corrected by V/R and U/R feedback loops, which is also known as Schuler tuning. Some people find the pendulum analogy helpful when considering Schuler tuning. We looked at the full list of platform corrections. And finally, we revised the full data flow, including Schuler tuning. We are not going to add anything more to this diagram. For our purposes, this is as complicated as it gets. However, we do need to consider how we initially set the system up by levelling it and getting it to point north before we start taxiing. This process is called alignment, and we will cover it in the next lesson.